today's lecture, we're going to be going over section 1.3, complex numbers, quadratic equations in the complex number system. Let's recall back to section 1.2 for just a second. Remembering back from section 1.2, we went over the quadratic equation. How do we solve quadratic equations using the formula? The formula was given to us in the last section, and we could tell a lot about the solutions of a quadratic equation by looking at what's underneath the square root symbol. b squared minus 4ac was called the discriminant. The discriminant will tell us how many solutions we have and what types of solutions. Recall, if everything underneath the square root is positive or greater than 0, then there will be two real solutions. If everything underneath the square root, or in other words, if the discriminant is 0, there is only one real solution. However, if everything underneath the square root is negative, taking the square root of a negative number, to this point was an impossible thing to do. Since the discriminant cannot be negative, that means there is no real solution. However, moving into the next section, section 1.3, we will discuss the implications of putting a negative underneath the square root symbol and how we can actually solve for solutions. They just will not be real. They will be what we will call now complex. So in section 1.3, we discuss what the square root of a negative 1 actually implies. X squared is equal to negative 1. Now, if we take the square root of both sides, you'll see that would mean x then equals the square root of negative 1. The square root of negative 1, as we know, there is no such real number that when you multiply it by itself, you'll ever get negative 1. But we're going to create this complex number so that that can come true. So we're going to call this I. So the square root of a negative 1, we're going to call I, which stands for an imaginary unit. It is not real, it is imaginary. In other words, if we square both sides, I squared, I is negative 1, and if we square that, negative 1 square root squared ends up to be negative 1. So by definition it works, but it's just not a real number. This new number is called the complex number system. Complex numbers will have this form, where a is a real part and b times I is going to be the imaginary part. All numbers that are real simply just have an a, and they have 0 in the imaginary part position. If there is an imaginary part, then the two combined makes a complex number. We can add and subtract complex numbers by just adding the parts that are alike, as if they were variables. If we added a complex number like a plus bi plus another complex number, c plus di, you simply add the real parts together, a plus c, so this would be the real part, and then we would add the imaginary parts together. In this case, b and di would be b plus di. Same thing with subtraction, just don't forget to distribute that subtraction sign. So the real parts would be a minus c, and the imaginary parts would be b minus d. So let's work on a couple examples together. I have this complex number, 3 minus 2i. Here's the real part and the imaginary part. plus 5 minus 4i. So we're going to add together the real parts. So 3 plus 5 is 8. The imaginary parts would be negative 2i plus negative 4i, which is the negative 6i. So that would be the complex number that is created from adding these two separate complex numbers. Let's try another one. Negative 2 minus negative 1. When we subtract a negative 1, you actually get a plus 1. So it's negative 2 plus 1. Then we have negative 3i minus negative 4i. So that's actually plus 4i. So negative 3 plus 4 is 1. We don't have to write the 1 in front of the I. We actually can simplify this and write it as just negative 1 plus I. We could do the same thing with multiplication. Let's look at some examples of that. Okay. Multiplication, we're going to always simplify. So for example, if I have 6i, we take the whole term and we distribute it to both parts next door. 6i times 3 is 18i. 6i times 9i is 54i squared. But as we denoted at the top of the page, I squared, by definition, is negative 1. This is a definition you should know and recall and memorize. Since I squared is equal to negative 1, we're going to replace all of this with negative 1. So that makes this 18i plus 54 times negative 1, which is 18i minus 54. Now, complex numbers are usually written with the real part in the front. So we're going to reorder these, and we're going to call this negative 54 plus 18i. Let's do it again. This time we've got a FOIL problem. 2 times 1 is 2. 2 times negative 3i is negative 6i. 4i times 1 is 4i. And 4i times negative 3i is negative 12i squared. Let's simplify. These are like terms, so it'd be 2 minus 2i. And as we know, this is negative 1. So it'd be minus 12 times negative 1. So this becomes 2 minus 2i plus 12. And if we combine these like terms, we get 14 minus 2i. One more, another FOIL problem. We're going to FOIL this out, and we're going to get 1 plus I times 1 plus I. So 1 squared plus 1i plus 1i plus I squared. So 1 plus, combine like terms to make 2i, plus I squared, which is negative 1. 1 plus negative 1 is 0. So this is my complex number. However, when there is a 0 in either of the parts, we can drop it and just call it by the other part, which in this case would be the imaginary. Now, dividing has some special rules. When dividing complex numbers, we don't like to see i's in the denominator. Remember, whenever we were dividing, we don't like to see zeros in the denominator. Another rule is we don't like to see i's in the denominator also. So we're going to need to get rid of any i's that might occur in the denominator. The way we're going to do that is by using what's called the complex conjugate. Complex conjugates are simply the exact same terms written with a different sign in between them. Look what happens when we multiply 2 plus 4i times its conjugate. When we FOIL that out, we get 2 times 2 is 4, 2 times negative 4i is negative 8i, 4i times 2 is 8i, and 4i times negative 4i is negative 16i squared, when we know this is negative 1. So this is going to become 4. Those are going to cross out. Minus 16 times negative 1 becomes 4 plus 16, which is 20. So when we multiply 2 plus 4i times its conjugate, we get 20. You'll notice 20 does not have an imaginary part. So when we multiply a complex number by its conjugate, what happened to the imaginary parts? They canceled out. The i's are no longer, leaving us with only real parts. So you'll only get a real number when you multiply a complex number by its conjugate. And that's a trick that we will use in order to get rid of those i's in any denominators. If you ever have an I down here, we can always multiply this number by its conjugate, and that will leave us with a real number in the denominator. So that's the trick we will use in the next few problems. Here, I'm asking you to find what is the complex conjugate of A plus BI. Well, the complex conjugate will be A minus BI. So when we multiply those two things together, you'll see that the middle terms will drop off. A times A is A squared. A times negative BI is negative A BI. BI times A is plus A BI. And BI times negative BI is negative B squared I squared, which when we simplify, you'll have A squared. Negative BI times negative 1 is actually positive B squared. So you'll be left with positive B squared. If we do another one, this time we'll use some numbers. You'll see that the same thing will happen and the middle terms will cancel out again. 4 times 4 is 16, negative 12i, positive 12i, negative 9i squared. These will cancel. This is a negative 1, so it's 16 plus 9, which is actually equal to 25. So let's do a couple of problems using division. Some of the goals that you'll want to remember is you're trying to get a real number in the denominator. In other words, I need to get rid of this I. The way we get rid of the I is we're going to multiply both the numerator and the denominator by the conjugate of the denominator. So I don't care what happens to the top. All I care about is getting rid of the I in the denominator. How I do that is multiplying the denominator by its conjugate. But make sure whenever you multiply the one level by some number, you have to do the same thing to the other level. We can't multiply the top by something different. So this becomes a FOIL problem on top and a FOIL problem on bottom. So let's go ahead and FOIL the top. 2 times 1, 2 times negative 4i, negative 3i times 1, negative 3i times negative 4i. 1 times 1, 1 times negative 4i, 4i times 1, and 4i times negative 4i. So you're going to see, since these are both equal to negative 1, this simplifies down to 2 minus 11i minus 12. 1 plus 16. See how we're left with only real numbers down here. So 2 minus 12 is negative 10. 1 plus 16 is 17. Now this is an okay solution, but generally speaking, we always want to write complex numbers in two separate parts. We want to split this fraction up into two separate parts. One part would be the real part, and the other part will be the imaginary part. So we're actually going to split this fraction up into two separate fractions. Negative 10/17 would be the real part, and negative 11/17 I would be the imaginary part. So this would be the more proper way to write a complex number, is by splitting up one fraction, which looks like one number, into two separate parts. Let's try another one. So again, what we're going to do is we're going to multiply this guy by the conjugate of the denominator. In order to get rid of this I down here, we'll multiply by its conjugate, 2 plus 4i. Remember, keep the same top and bottom. So let's FOIL out the top. 8 plus 16i plus 6i plus 12i squared over 4 plus 8i minus 8i minus 16i squared. So you'll notice both of these become negative 1. So that gives me 8 plus 22i minus 12 over 4 plus 16. 8 minus 12 is negative 4 plus 22i over 20. And again, we want to split these up into real and imaginary parts. So I'm going to have negative 4 over 20 plus 22 over 20i. Now you're going to notice at this point that there are some simplifications that can happen. Negative 4 over 20 will simplify to negative 1/5. 22 over 20 will simplify to 11 over 10. So sometimes a real part can simplify further than an imaginary, or vice versa. So always simplify each fraction down as far as possible, even if that means the denominators don't match. Now moving forward, we're going to describe the different powers of I. Okay? So at the very top, we've got I to the first power. I to the first power is simply just I. By definition, that's the square root of negative 1. I squared is going to be the square root of negative 1 times the square root of negative 1, because it's I times I. And when you have the square root of negative 1 times itself, you're simply just left with negative 1. I to the third power is going to be I times I times I, or a simpler way of writing it would be I squared times I to the first. By the definitions we've already used up here, I squared is negative 1. I is just I, so we're left with negative I. I to the fourth, if I can use something that I've used up here, I to the fourth is simply just I squared times I squared. By definition, I squared is negative 1. So if we multiply negative 1 times negative 1, well, we get positive 1. I to the fifth, by definition, is I to the fourth times I. I to the fourth is 1. I is just I. 1 times I is I. I to the sixth is I to the fourth times I squared. I to the fourth is 1. I squared is negative 1. 1 times negative 1 is negative 1. I to the seventh is I4 times I3. By definition, I to the fourth is 1. I to the third is negative I. So we get 1 times negative I is negative I. So you can see there's a repeating pattern that is occurring. I, negative 1, negative I, 1. Let me write that again. I, negative 1, negative I, 1. And then they repeat again. I, negative 1, negative I. So you can guess what I to the eighth would be. It would be 1. So every fourth power, I to the first, second, third, fourth, I to the fifth, sixth, seventh, eighth, I to the ninth, 10th, 11th, 12th. And this repeating pattern would go on for infinite. Every fourth power, every power that is divisible by 4 will be equal to 1. The remainder will tell you what it's equal to. For example, 16 is divisible by 4, so therefore I know the answer is going to be 1. By showing it to you longhand, we could say, well, this is I to the fourth, well, 4 times, right? Because 4 times 4 is 16. By definition, I to the fourth is 1. So this is the same thing as 1 to the fourth power, which is 1. But I could have told that because 16 is divisible by 4, so therefore I know its answer is going to be positive 1. Let's try 26. 26, how many times can I bring I to the fourth up to? Well, I can only bring it up to the 6th power, and then I need 2 more, right? Because that's I to the 24th power times I squared. That's the remainder. Anything to the 4th power is simply just going to be 1. 1 to the 6th power is just 1. So really all we have is just I squared left over, because I don't care how many times the 4 goes into it. All I care about is what the remainder is, because I to the 4th power to any other power will always be 1. So all I really care about is the I squared, and by definition, I squared is negative 1. I to the 33rd. So we're going to take I, and that's going to bring me up to the 4th power. I'm going to bring that up to the 8th power, because 4 times 8 is 32. So this is I to the 32nd power. So I'm going to need 1 more to bring me to 33. I to the 4th is 1. 1 to the 8th power is 1. And 1 times I is I. 1 more. I to the 43rd is I to the 4th to the 10th power, because that's 40. And then I'm going to need 3 more. I to the 4th is 1. 1 to the 10th is 1. And by definition, I to the 3rd is negative I.